Procedural mesh generation can allow you to create 3D models and geometry dynamically at runtime. This means that you can generate everything, from terrain to houses. In this video, we'll be walking through the core concepts of how to generate a procedural mesh, and then I'll show you how to create one in Unreal. To understand procedural mesh generation, we need to know what a mesh is. So a mesh is a 3D model that is created from a set of vertices and triangles. Now each vertex is connected by triangles, and the triangles give the model its surface, whereas the layout of the vertices can help give the model its shape. Let's look at how the computer actually stores the data for the triangles and vertices for our mesh. So here, all of the vertices get numbered as they're added to an array. First, we start our first vertex would be number 1, then the second vertex number 2, the next 3 and 4. And we want to keep these vertices in a specific order so that we can easily keep track of what we're doing. Really, you could have these numbered in any way, but that would then make making triangles more difficult. And how the triangles are stored is a list of references to the vertices. So a first triangle would list 3 vertices for the vertices that make up that triangle. So here we have our first triangle, and usually they're created in a clockwise manner, but that may differ based on what program you're using. But here for a first triangle, we would have the values 1, 3, 2 for those vertices that make up the triangle. And then for the triangle here on our right, we would have the values of 2, 3, 4, and that would make up the second triangle. So when we go ahead and implement a procedural mesh, we'll have to track our vertices and which vertices make up which triangle. All right, here in Unreal Engine, I have an empty map, and I've placed a cube for reference. Each side of this is 100 units long. And in this map, I've set the default pawn class to spectator. So that way when we play, we can freely move around. Now in this map, we're going to try to create a procedural mesh. We'll start by creating a plane. So if we go to our blueprints, can create a new blueprint class from actor, and we could call this BP procedural plane. You open that up. Now in here in our procedural plane, we'll be using the procedural mesh component. We'll search procedural mesh. This will allow us to create the mesh using triangles and vertices during the game. We'll go to our event graph. We can delete all of the events except our begin play. So on begin play, we will generate this plane. Now in here, we will want to first determine all the vertices for all the points of our plane. And to do that, we'll first just put debug spheres in the world to make sure that we're placing the points at the correct positions. So that if we right click, we could type debug sphere. And we have this draw debug sphere. So we could test what this will look like. I hit play. See, we need to add our procedural plane into the world. It's at 0, 0. Now hit play. Add the flash of the debug sphere. Let's turn up its duration. Let's do 5 seconds. Change its color. There. Now we have our debug sphere at this point. So let's go through and put debug spheres on all the points where we want the vertices for our procedural mesh. Let me disconnect this. So we'll want some X direction and Y direction for our procedural mesh here. For the X and Y, let's call it our resolution. So that'll be the number of points in that direction. Well, here we can make a new variable x resolution, and this will be an integer, and a y resolution, which is also an integer. Let's drag both of those out so we have them. Now we can create a for loop to iterate through all of our x and y sizes here, our resolution, in order to place debug spheres at various points along our x and y directions. So we'll take our x resolution -1, plug that into our last index, and let's move this down, and our y resolution -1, and we'll make another for loop for our y. Now we can plug in our first loop into our second loop, so we're iterating our x for every single y, and plug in our debug sphere into our second loop, and we can change the position of these debug spheres based on our loops. So our first index, let's plug that into our y, and our second index, plug that into our x. Now let's change our radius down. Let's do a radius of 5. So these spheres are smaller and we can see exactly where they're at. I'll also increase their thickness a bit. Let's say 2. If we go back, hit play, we can see nothing changed because I didn't set our x and y resolutions. So our y resolution, let's say, is 5 and x is 5. Now let's test that out. You can see all our positions here are really close to 0. So that's because we're using values of 0, 1, 2, 3, and 4 for our locations. Let's go ahead and add a scale to multiply by those indices so that we can spread out our points. So let's have two different ones. Let's call it x scale, and this could be a float because it could be any value, and a y scale as a float. Compile. Let's set our default to 100 and 100 on each of those. Now let's apply these in our y loop, drag in our y scale. We can multiply our y scale by the current index and plug that into our y position of our debug. And we'll do the same thing with our x. Drag in our x scale, multiply by our index, and plug that into our x. Now if we hit play, there we go, we can see our points have spread out by 100 each. Returning back to the blueprint. Now that we have these set vertices, we can do something to normalize our vertices. Currently, as we change our resolutions, our size will also change. So we can normalize our indices to be between 0 and 1. So to see that happening, let's first make our values private and instance editable, so that way they can be modified in the level, but not by other blueprints. So let's look here. We can have our x, y resolutions and scales. If I hit play and see we have our 5 points along each direction. If I change the resolution in x to 9 and hit play again, you can see it actually got bigger. So we don't want our resolution to change the actual size of our mesh. The resolution should just say how many points are in that direction, and our scale should be the thing that influences the overall size of the plane. So back here in our blueprint, what we can do is we could take our index and divide this by our y resolution minus 1. So this will help to normalize our y values. So our first y value in our loop, or our first index, will be a 0. So we'll do 0 divided by this number, so we'll get 0 for our first one. And on our last index, let's say y resolutions is 5, so our last index is 4. If we follow that index up, we'll have 4 divided by 4 is 1. So there we're remapping our y resolution from 0 to our y resolution to a range of 0 to 1 by normalizing it by our last index that we're using. We can plug this in, and we could go ahead and copy and paste this below to also use this normalization for our x. We'll replace the y resolution node with the x, and we'll divide it by our x resolution, plug that into our scale. Let's clean this up a little bit, make it a little more legible. I'll move our x loop farther over. So first we're doing our y loop. I'll move our x down a bit to visually differentiate them. Now if we hit play, we only have the 2 values here, so this currently is not correct. We're only putting our values at 0 and 1. And that's because we're using integer math here, so we're only getting integers out. So we were trying to map it from 0 to 1, but integers could only be 0 or 1. We cannot have intermediate values. So we actually need to convert these to floats. So we'll do type float, and there should be a 2 float integer. And for this one, 2 float. So the floats will allow the division to end up with a value between 0 and 1 and not limit it to only 0 and 1. We need to do the same thing. I'll copy these conversion nodes up to our y loop. Connect those conversions, delete this alt division, and connect our y scale. And to straighten these connections here, I'm hitting the Q key. So now we should be able to get values between 0 and 1. So let's go back to our map and hit play. There we go. So now we're getting all our values on a grid between 0 and 1. And then we multiply that by our x and y scale. Let me turn up our duration. Let's do it to 30 seconds. You can see it a little longer in the map. So now as we change the x resolution, let's change that to 17, hit play. We're just adding a greater resolution of points in that direction, but not changing the overall scale of the mesh. And then if we change our x scale itself from 0 to, let's say, or from 100 to, let's do 500, we should actually scale the size of the mesh. And if we bring our x resolution back down to 2, but keep x scale at 500, we should only get 2 points along that longer distance of 500 units. There we go. We see our resolution and our scale are both working correctly for our plane. Let's reset these default values to 5 points for our resolution and 100 for our distance. Go back to our procedural plane. So here we're correctly creating our vertices, and we're visualizing them using these debug spheres. Let's go ahead and I'll Control-Alt to select everything, and I'll deselect this begin play. I'll collapse this to a function, and let's rename it as determine vertices. So this function will determine the vertices for our plane. If we open that back up, we could clean this up a little bit. I'll move this back over. Let's add some local variables so that we could keep track of this if we need to come back. So here in our y loop, we did this division by our resolution and our y scale, or multiplied by our y scale. Now this end result float is sent over to be our y vertex position. So let's just convert this to, or promote this to a local variable. This will be our y. Connect that in. And we can disconnect it over here and call that as our y. Let's do the same thing with our x here. Drag off here, local variable x. Connect that up. And drag in our x variable. There we go. So we have our x and y creating our debug spheres. Now let's go ahead and look at how the procedural mesh actually needs to obtain these vertices. And then we can, instead of doing our debug sphere, actually start creating the vertices for our mesh. Let's go to our event graph. And in here, we can right click and create section. And this is create mesh section for our procedural mesh. Now this needs various arrays of information to create the mesh. One of them is our vertices. And this is a array of vectors. So every vertex has a vector that says where it is. And we collect all of those different vertices into an array and use that to create our mesh section for our procedural mesh. So let's have our determine vertices on the first node here. We can have it give us an output, have this function give us an output. Let's call it vertices. And we'll change the type to vector array. Now, if we go back to the event graph, we'll see we'll have this vertex vertices output, and we can connect that into our create mesh section. Currently, I'll leave this disconnected so we're not creating anything here, since we don't have our triangles or any other information in there yet. But our vertices are hooked up. But now in our function, we'll have to find a way to actually output this array of vertices. So to do this, we can drag off our vertices and promote it to a local variable. I'll call this local vertices. So we could keep track of every vertex in this local array. If we go over to our debug sphere, instead of using our debug sphere, we could drag out our local vertices and add a new vertex to it. And I'll split this pin. Our new vertex can use these same x and y's, and then we'll leave the z's at 0. I'll move our debug sphere in case we want it later, just below. And we can hook up our add new vertex, or add new vector to our array of vectors for our vertices. Now we need to connect our return node, and this will occur after our outside y for loop is completed. So when all the loops are done, then we'll return the array of all the vertices we've created. There, so now we have our array of vertices back to our event graph. Now we need to look at creating our triangles. So let's create a new function like we have for determine vertices, but we'll use it to determine our triangles. Create a new function and call it determine triangles. And in our event graph, we can drag in our determine triangles, connect it in. Let's not connect our mesh yet since we don't have our triangles out. Now our triangles need to be determined based on the vertices. We have to know what order of vertices to use for our triangle. And our function determine triangles needs to output a triangle array here for our mesh to use it. So this triangle array is an array of integers, and it needs to be a multiple of 3 because every triangle has to have 3 integers indicating the points of the triangle. Those points are references to the vertices themselves. So in our determine triangles function, we can add an input and an output. Our input will be the vertices, and we'll leave that as this vector array. And the output will be the triangles. And this will be an integer array. And then in here, we'll have to determine the triangles. We can look at our first triangle to get a good idea of how we want to track the vertices for the first triangle, and then try to use that first triangles method for the rest of the triangles in the mesh. So let's go to our procedural mesh level, and let's change our resolution just to 2 and hit play. And we're not showing our debugs anymore, so let's go back to our determined vertices and plug back in our debugs so we can see them. Hit play. Now in here we have our 4 points. We'll want to create triangles between our first 3. So this will be this is vertice 1, 2, 3, 4. We'll create our first triangle between 1, 2, and 3. And the order of our triangles here matters, so we'll go in clockwise manner. So it'll be 1, 3, 2. We'll go back to our determined triangles. Let's make a note of our 1, 3, and 2 for our first triangle. Now we can drag off our vertices, and we can get copy. And this will allow us to get particular vertices in our array of vertices. And this get will be the index of that vertex. Now we can use that for any array. So we could also do that for our triangles array. And we can drag off our triangles here and create a new local variable. This will be our local triangles. These will be the triangles that we can determine and output. Now this local triangles, we will want it to be overall a length of 6 times the number of squares we have. Now let's look at our procedural mesh and see why this is. Let's increase this to a size 3 and 3. We hit play. We can see that we have 2 triangles in every square, and the triangle will have 3 points. So 3 for this triangle and then 3 for the next triangle. So we have 6 points per square. And here we have 1, 2, 3, 4 squares. So we'll have to have our x is 3 minus 1 and our y, which is 3 minus 1. So we have 3 points, but there's 2 squares. So overall, it'll be our dimension minus 1, then times 6 for our 6 references for the triangles within each square. So let's go back to our procedural plane. And let's first create just an empty array for these local triangles. So let's create a for loop. Now this for loop, we will iterate through our x resolution, and we'll also iterate through our y resolution. So for our y resolution, minus 1, and our x resolution minus 1. And we'll multiply those together. So in our example, we had the 3 vertices, and we'll do -1 to reference the squares. So 3 on our x, -1 is 2 squares for our x, and same for our y. And then we'll multiply those together to get the overall number of squares in both directions. And then we'll, off of that multiply, since we're doing a for loop and we're starting at index 0, we'll -1 to end an index earlier. Now in here, let's add just empty values. So we'll just use the value 0 to our local triangles. So this will just give us a big array of the proper size of triangles just as value 0. Let's put a comment around this. Let me delete these other comments. I'll keep the 1, 3, 2. This will be create empty triangle array. So now this triangle array will have no actual data information in it, since we're just saying every triangle uses the vertex of 0 for every single point on the triangle, which is not correct. But now we have our empty array. So now we can modify any element within that array. So let's try setting our very first triangle in this array. Our first triangle, let's see, we know should be vertices 1, 3, and 2. Let's grab our local triangles and let's, instead of add, let's set array element. So set the array element at a certain index. So at index 0, our first one, let's set our item to be 1. So that'll be our first vertice, the first vertex. And then we'll set another array element. This will be our first index, so our second, one in the row. And we know this should be our vertex 3. And add a third. And this one will be index 2. And our element will be 2. Let's plug that into our ending node here, our return node. So we're only setting, this is our first triangle. And let's connect this to our completed from creating our empty triangle array. Now let's go ahead and generate our procedural mesh just using this one triangle. So we have all our vertices created, but only the one triangle. Let's go back to our event graph and we can connect this information back up to our creating the procedural mesh section. And let's see how this works. So here it looks like our triangle is not in the correct spot. We'll move our reference cube. So we're using the wrong vertices to create this triangle. Back here in our procedural plane. So here it looks like we actually used the wrong vertices, this 1, 3, 2. We should start at the number 0. Our first vertex is 0, not 1. So 0, 1, 3, 4. So in this case, we're using 0, 1, 2, and then 3. So 0, 1, 3. We hit stop. So 0, we'll do 3, and 1. Now when we hit play, let me move our mesh down so we can see. Hit play. There we go. So now we're creating that first triangle in this first square. So we had some of the wrong vertices because we had changed the resolution. So if I change this resolution to 4, now we'll be using the wrong triangles again. If I hit play, we're not creating any triangles. If I decrease it down to 2, we're still not creating any triangles. So we're trying to create the wrong triangles. And we need to We go back to 3 and 3, we have it right. So what we need to do is the actual numbering of the vertices changes based on how many points there are. So we need to take that into consideration. And we can't just hard set our triangle values here. It needs to be based on our resolution and how many triangles there actually are. We have this first triangle for that square. Let's try to make the second triangle for that first square. And then we'll look at expanding that for all squares in the mesh. Let me expand this. We have our first triangle. And then here we can have our second triangle. Well, let me move the comment. That one's the first triangle. This one's the second. Now the second triangle won't use our first point. So here, the second triangle will be among these 3 points. So this is 0. So 1, 3, and 4. So 1, 3, and 4. 1, 3, 4. And then our indices continue after this. So 0, 1, 2, 3, 4, and 5. So the first triangle uses the first 3 indices in the triangle array. The second triangle uses the next 3. And then the third triangle we'd use the next 3 and so on. Let's hit play. Well, I need to connect this up to our return node. Going to the map. When we hit play, let's see, we're only still drawing the one triangle. Let's see what our problem is. We should have our proper 1, 3, 4. So I don't think this triangle array is created right. We never multiplied this by the 6 that I had mentioned earlier. This is only the number of squares, not the number of triangle points. So let's just to test that and see. Let's get our local triangle and say length. So I think this will be a length of 4. Let's make print. This should be a length of 4. Let's go hit play. Yeah, so that is a value of 4. So we're creating the wrong number of triangles up here. So then when we're trying to set them, we're getting the wrong values. So let's go ahead and add in this multiply by 6. And this will be, let me undo that. This will be after we get the number of squares, and we'll multiply that by 6. Since there are 6 triangle points in a square, and then we'll still have our -1 for our last index of the for loop. We'll still print out that length. Now if we hit play, there, so we should see the new square, and it said 24 triangle points. So 6 for every square in our mesh. Perfect. Can delete this print. Now let's look at how we can make these triangles appear for any sized mesh. So right now, if I go ahead and change the resolution, we'll be getting the wrong triangle points. So change that back to 3. So we're getting the correct triangle points only when we have 3 points, 3 vertices in each direction. This is our square of triangles. So we have our 2 triangles making that square. We'll want to do that for every square in the mesh. So we'll need some for loops in here. Let's create a for loop and iterate through our y's and our x's. So first let's drag in our completed here. And this will be, let's only focus on our x direction first. We'll have our x resolution, we'll say minus 1 because of the for loop, but then also we want to iterate through the number of squares in the x direction, which is 1 smaller than the number of points in the x direction. So we'll subtract another 1. So we'll do -2 for that x resolution. Bring in our loop body. So to help make these triangles dynamic for each of the different squares, what we can do is track what index we're at and track what vertex index we're at. So what triangle index and vertex index. So we'll create 2 new local variables, and this will be triangle index, and this will be an integer. And we'll create another one, and this will be vertex index. Well, we can drag those out. So our triangle index will correspond to these indices for what triangle we're at, and the vertex index will be what vertex we want to assign to that point on the triangle. And I'll disconnect our return node from being in our loop and instead move it to when we're completed with the loop. Now here in our triangles, for every square, we're generating 2 triangles with 6 points. So our triangle index will start at a value of 0. And then by the time we're done with this, we'll have added 6 more. So let's go ahead and try to plug in this triangle index. I'll delete the vertex index for now. So our first triangle index when we start the process is 0. So that matches our first one here. And let's scale these out from each other. Our second point here has a triangle index of 1. Our triangle index is currently 0, so let's say +1. Move all this over so we have some more room. We have our triangle index +1, and this next one is 2. So we'll have our triangle index +2. The third will have triangle index +3. Scale these over even more. There we go. And then we'll follow this pattern, triangle index +4 and triangle index +5. And then we'll go, when we go back to the next index in the for loop, now our triangle index is 0 again. However, we've already set 0, so we need a way to increment our triangle index. So at this point, it should be a value of 6. So at the end here, after we add the 6 points, we can just say triangle index +6. So we'll increment this ourselves. Instead of having a for loop or something increment it for us, we'll say our triangle index is +6 and set our triangle index to itself +6. So that way in our second, when we loop here, our triangle index was 0. And then now we're saying it's 6. So when we loop, we'll go back to the beginning, triangle index is 6, and we'll set our we'll start on our next 2 triangles for the next square. Now we need to see how we can determine our vertex point. So let's try to go through this first triangle. We'll grab in our vertex. Our first vertex, we haven't set it to anything, so at the beginning it's equal to 0. So that seems correct. So let's plug that in. Our next vertex is a value of 3. However, this will change depending on how long our resolution is. So this value of 3 is equal to the size of the resolution. This will be the first point that loops into the next line. So let's go ahead and look at here. So we'll have 0, 1, 2, 3. It's the point above our starting point. So it'll be our starting point plus our x size, so plus 3. So vertex plus our x resolution. Plug that in. This next one is 1. Let's look here at our reference. So it'll be our starting point plus 1. We're just moving 1 to the right. So let's just call that our vertex index plus 1. Moving over, here we have our 1 again. We use that same vertex point in these two different triangles. So I'll reuse that. And now here is our 3 again, which is the same as our 3 from earlier, our vertex index plus our x resolution to go up into the next row. Then our last one is item 4. Let's look at this in our reference. So this will be 0, 1, 2, 3, 4. So it is our starting point plus our x resolution, so to go into the next row, plus 1 to move over. So it'll be our vertex index plus our resolution plus 1 to move over by 1. Then triangle index plus 6. Let's see, do we need to increment our vertex index? Yeah, so here our vertex index will help us track the portion of the mesh that we're in. So for the first iteration through, we're at vertex 0, and we determine all our neighboring points. Then in our next square, we'll be at vertex 1, determine our other points for the triangles. So we'll just increase our vertex by 1 to go to the next one, to the next vertex. Say vertex plus plus, and connect that in. Over here to the beginning. Let's go see what this looks like now. Oh, here I've been thinking about our x and y is the opposite of what they are. So we've actually gone down our row to the left. This is our x direction. So we filled in our next square. Let's go ahead and try to increase our x resolution. Let's increase this to 5. And we should be looping through all 5 of those. There we go. So 1, 2, 3, 4, 5. We're making 4 squares of triangles. So we'll have 1, 2, 3, 4, 5, 6, 7, 8 triangles in there. Now we need to loop through all of our y directions. We'll go back to our procedural plane. Now in here, we'll need to iterate through our y direction as well. So I could copy our current x for loop. Instead of our x resolution, let's use our y. And let's connect this between our empty triangle array and our x loop. And let me move all this over a bit. All right. Now in here, let's see how this works, but we'll have to make some additional modifications, but let's see what it's doing now. So we're not doing anything different. The triangles we're placing are not actually being incremented using this y loop yet. So we can try incrementing our vertex index in our y loop as well. So in here, we're actually leaving early out of our loops. We're returning out of our x loop here. Let's move that instead to our outside loop. Let's see how this is running. We're almost creating all of it. We're just not getting that very last square. Go back to our plane. So we're not actually incrementing properly through our vertex indices when we reach our y loop, we need to, in our x loop, when our x loop is finished, we need to move to the next vertice. We're currently overlapping our previously made triangles with new triangles. Since we're not incrementing our vertex when we go to our next y loop. So if we increment our vertex index plus plus at the end of our x loop, can compile and save that. Let's hit play. Now we're creating all of the triangles within our mesh. Let's go ahead and try making this larger and see if that is properly responding to our changes. It looks like it is. Let's make our scale bigger so we can see it a little better. Let's make this much larger. Let's do 1000 by 1000. Perfect. So now we're making this mesh procedurally, and we can choose how big it is, how much resolution the vertices have in it. So if we wanted to increase our resolution, let's do 100 and 100. Now we can have many more vertex points in this grid. It's a little much. Now all our debugs are copying each other. It's a little frozen because the debugs take a long time to render. We go into our procedural plane, determine vertices. Let me delete our debug. Hit play. There we go. So we have a lot of vertices in our procedural mesh here. If I back out of this, I can hit F8. Instead of lit, let's look at the wireframe. So here we could see all of the vertices that we've created and all the triangles we've created in our procedural mesh here. And I'll switch back to lit mode. And there we go. So now this is the starting point of being able to create the mesh from the vertices and triangles. And here I'm realizing we never actually used these vertices in here. We didn't need to determine them based on the vertices themselves, just we have to know the order of them. So we could go ahead and delete this input. And going back out to our event graph, here we can create the mesh using our vertices and triangles, but we can also do other things like create the UVs and normals. So here to get our normals, we can actually have Unreal Engine generate them for us. And here if we search tangents, we can search for a calculate tangents for mesh, and this will create our normals and tangents based on the vertices, triangles, and UVs. So we don't currently have the UVs yet, but let's hook this up. We can plug our triangles in, plug our vertices in, try to reroute these to clean it up a bit, and then bring out our normals and our tangents into our mesh that we're creating. Now this should help the light look a little better when hitting our plane, as it'll have the correct normals. Now let's see how can we generate this UVs. These UVs will be values from 0 to 1 in each direction along our plane. So let's just, for this example, let's use our X direction as our U's and our Y direction as our V's. Now, these UVs can kind of be applied any way you want onto a procedural mesh, but here, since we're doing a plane, let's do our X's and Y's as our U's and V's. Now, each of these UVs, it's a vector of UVs that corresponds to a UV at every single vertex. So what we can do is generate the UVs when we generate the vertices. So let's rename our determine vertices function. Over here on the left, determine vertices, let's just say and UVs. And from this, we can add a new output. This will be our UVs. And our UVs will be a set of vector 2's. vector 2D. Can connect that in to those UVs and these UVs. Now in our determine vectors and UVs, we'll have to actually determine the UV for every vertice in our mesh. From this UVs, let's promote this to a local variable here. And we can call our new variable local UVs. When we add our vertice to our list of vertices here, we can actually now add a UV into our list of UVs at the same time, since we know what vertice we're currently at. So here we'll look at add. We can add a UV for this vertice. Let's go ahead and split this pin. So we need our X and Y. This is actually our U and our V for our UV. And we can convert our X and Y into our U and V. So here are X and Y, since we've multiplied it by our X scale, these will no longer be between a value of 0 and 1 for our U's and V's. We'll need to access our normalized X and Y's before we multiply it by our world scale. So let's go ahead and promote those to local variables earlier so we can access them here at the end. So in here, before we multiply by our X scale, let's drag this up and promote this to a local variable. This will be our normalized X. And then we multiply our normalized X by our scale to get our X. Let's do the same with our Y. Promote this to a variable, normalized Y. And multiply our normalized Y by our world scale to get our Y value. Perfect. Now at the end, instead of our X and Y's, we could just plug in our normalized X and normalized Y, as those will be values between 0 and 1 at every point, so that's exactly what our UVs are. There we can generate our UVs. Let's go back to our event graph. We should be generating all these things correctly. Let's make sure that our plane still generates. There we go. We have our plane, and it's been given this default grid by Unreal. So Unreal's recognizing that we have proper UVs in there. Now what we could do is, after we create this mesh, we can use this procedural mesh component and we can set the material. So we can choose any material to put on this procedural mesh now. Let's search for grid gray, and this is the prototype grid gray, and test that. And we should get our gray grid across our plane. It looks like it's all fitting properly across our grid. Now that's how we create this procedural mesh here. So at this point, we've completely created a plane. So if you want to use a plane in any circumstance, you can use that here. But you could also just have done a plane with the base plane primitive. But now we can modify this procedural mesh in any way we want to get something like terrain, or you can generate them in a different order to create spheres or different shapes. Now let's go ahead and see if we can test out and modify this to be somewhat like a terrain. So in our determine vertices function, we can change the z height value. Let's set our z height value equal to x, just to see what that does. So our height should be equal to our x, so that should slope our plane. Yeah, so in our x direction, as x gets bigger, we slope it upwards. Let's make this, let me drop down the resolution 50/50 so it goes a little faster, and our scale, I'll make this much bigger. I'll add another order of magnitude up to 10,000. Hit play. So we have a much larger plane. Now instead of adding in our X, we can start adding in some random noise. So let's add in a random float in range. Now here I'm not going to set it up with the seed, but you could set it up with a seed so that you generate the same procedural plane every single time. And here I'll do a range of 0 to 200. And let's use that for our Z. And that will give us this jagged terrain here. So this is a purely random terrain. So this might be a bit more jagged than you would want. But you could do other sorts of things like add in Perlin noise or other sorts of noise like Voronoi noise to kind of soften these sharp changes that random values give you. But you could also do other things like let's take our X and let's say sine of X. And let's plug that into our Z. So now we should be getting a sine wave along our Z. Let me make this bigger. So let me multiply it by, this would be an amplitude here. After our sine of X times something, this is an amplitude for the wave. So let's say our amplitude is 100. And hit play. So now we're getting a sine wave along this based on our resolution and our points. You could also take this sine wave and use this normalized X instead of the X. So we just get one big sine wave that's along the entire grid. But let's see, our input is currently 0 to 1. Our sine should be like 0 to 360. So let's do times 360. Here we go. So now we should be getting our sine wave along our X direction here. You can see that. Let's make our scale a bit bigger. Let's say 1,000 for our amplitude. There we go. So now we're getting our sine wave. And you could add, on top of that, add our noise, or our random values. Let's see what that looks like. We're getting massive spikes up and down, so we probably don't want to multiply that. We want to add those. So we add in 200, not multiply it by 200. Now we're getting sort of large hill from our sine wave and then lots of little bumps from our random noise. So you could kind of go ahead and start modifying this simple plane in any sort of way using different rules. And these rules are what makes up procedural generation itself. So you can go ahead and experiment with this any sort of way you want. Adding in a y value for our sine as well. So add that in. So we should be using our sine wave on our X and our Y. You can kind of go ahead and play with this any sort of way you want to get kind of terrain that you're looking for. Now, if you like this video, please hit the like button, subscribe to the channel. Let me know if you'd like to see under any other sorts of procedural generation techniques. In the future, I'll be going over other use cases for procedural meshes, and I'll look at generating cylinders and other rounded objects with procedural meshes rather than big flat planes. But let me know if you'd like to see anything else. Otherwise, I'll see you in the next video.